Engineering, Vidyavardhini's College of Engineering and Technology would like to welcome all of you to the short-term training program on geotechnical engineering aspects in infrastructure project. This program will bring together professionals, researchers, and enthusiasts in geotechnical engineering to develop the critical role it plays in infrastructure development. And over this course of the program, we'll explore the cutting edge research, innovative solutions, and practical challenges in geotechnical engineering with our distinguished speakers, interactive sessions, and thought provoking discussions. This event promises to be a platform for learning, collaboration, and innovation. I encourage everyone here to actively participate, exchange the ideas, and make the most of this opportunity to connect with experts and peers from across the field. Without the further delay, let us begin our journey into the fascinating world of geotechnical engineering. To start with, I would like to invite Mr. Arbaz Kazi, Assistant Professor, Vidyavardhini College of Engineering and Technology, to share the inaugural address. Sir, please take over.
Hello, good morning. Good morning, everyone. It gives me immense pleasure to welcome you all to this 1 week online short-term training program on geotechnical engineering aspects of infrastructure project. This project aims to provide a platform for knowledge uh, and skill enhancement in one of the most critical and evolving areas of civil engineering. Before I proceed, let me first take the opportunity to extend my heartfelt gratitude to our respected dignitaries who have joined us today. First and foremost, I would extend a warm welcome to our head of department, Dr. Ajay Radke sir, whose leadership, dedication, and encouragement was instrumental in organizing this program. Next, I would like to warmly welcome our esteemed principal, Dr. Rakesh Imte sir, whose vision and support has always been the cornerstone of academic excellence in our institution. And most importantly, it is my distinct honor to welcome our esteemed speaker for the session, Dr. Jitesh Chavda sir. Sir, your vast experience, knowledge, and in the field of geotechnical engineering makes you the perfect guide for today's session. We are excited to learn from your insights and expertise, which will undoubtedly enrich our understanding and broaden our perspectives. As we know, geotechnical engineering plays a very major role in the development of infrastructure projects, right from the soil classification, slope stability analysis, selection of foundation types. The role of geotechnical engineer thus plays a very important in shaping the sustainable infrastructure. With this, the STTP aims to delve into those aspects and provide the participants with a comprehensive knowledge of geotechnical engineering principles relevant to infrastructure projects. To all the participants, faculty members, students, and industry professionals, I extend my heartfelt welcome. Your enthusiasm to learn and grow is what makes such programs meaningful and impactful. I am confident that the sessions planned as part of this program will ignite new ideas, foster discussions, and provide valuable takeaways for all of us. Once again, I welcome you all to this event. Thank you for your presence and support in making this program a success. Over to you, Aishwarya, ma'am.
Thank you, sir. Now I would like to call our HOD of Civil Engineering Department, Dr. Ajay Radke sir, to address the attendee.
Good morning, everyone, and I wish you a very happy New Year 2025. Honorable Management of Vidyavardhini Trust, respected Principal Sir, esteemed speakers, HODs, faculty members, and my dear friends. It gives me immense pleasure to welcome you all for the STTP on geotechnical engineering and aspects for the infrastructure projects. Today marks the beginning of an enriching journey where we'll dive into 12 a critical role geotechnical engineering plays in shaping infra projects. Geotechnical engineering field plays a pivotal role in the planning, design, and implementation of infrastructure projects, addressing the challenges such as soil stability, foundation design, slope protection, and much more. Through this program, we aim to equip you with the advanced insights and practical solutions to tackle these challenges effectively. The STTP will feature a series of lectures, discussions, and case studies delivered by eminent speakers from academia and industry. We hope these lectures will not only broaden your technical understanding, but also inspire innovation and critical thinking. As we embark upon this program, I encourage all of you to actively participate, interact, and share your ideas. Let this platform serve as a collaborative space to exchange knowledge and build networks that will benefit us all in the long term. So, once again, I welcome each one to this program. Let's make most of this opportunity and contribute to the advancement of geotechnical engineering in infrastructural projects. Thank you. Wish you all a fruitful and a rewarding experience ahead. Thank you, experts, and over to Aishwarya.
Thank you, sir, for your valuable words. Now we would like to start the session. So the session will be on image application. So Arbaz sir, can you please proceed?
Good morning once again. So before I start with the session, I would first like to introduce the speaker for the first session, Dr. Jitesh Chavda sir. Dr. Jitesh Chavda sir is working as assistant professor in Geotechnical Division, Department of Civil Engineering at SVNIT, that is National Institute of Technology, Surat. Sir has obtained his PhD degree from IIT Madras and in geotechnical engineering. He holds diploma and bachelor's of degree in civil engineering from University of Mumbai and MTech in geotechnical engineering from SVNIT Surat. He has worked as trainee engineer and has carried out various projects involving deep excavation. He has worked as project associated at IIT Roorkee and served as lecturer at Rizvi College of Engineering. He has published several papers in reputed journals, national and international conferences. His area of research includes computational geomechanics, conservation of heritage structures, experimental geotechnics, and image analysis. He has received Best Paper Award in Indian Geotechnical Conference 2019, Institute Gold Medal for securing first position at MTET, and Mr. and Mrs. M.D. Desai Award of cash prize of 15,000. Emerging Scientist Award in INSO Awards in 2021. Best Paper Awards in 3-day International Conference on Advancement in Structural and Geotechnical Engineering in 2022, which was organized by Indian Geotechnical Society. Then again, Shri B.N. Gupta Biennial Award by Indian Geotechnical Society in the year 2023 and the recipient of ISSMGE Bright Spark Lecture Award in the year 2023. He also serves as a secretary of technical committee of 301 historic sites, International Society of Soil Mechanics and Geotechnical Engineering. So I would now like Jitesh Chavda sir to take over the session and start with your session. Thank you, sir.
Sir, you're not audible. Sir, you're not audible.
हेलो चावड़ा सर शेयरिंग बंद किया हेलो सर कैन यू हियर अस
Good morning, sir.
Yeah, am I audible now?
yes
You are
sir
not audible now.
हेलो
Hello.
सर हेलो क्या प्रॉब्लम हो रहा है
Yeah. Am I audible there?
yes sir right now you are audible but it is very I mean the audio and video is very stucking To the participants, we'll just start in 5-10 minutes as there is an issue with the speaker side.
Okay, ma'am.
Hello. Can someone confirm that my voice is audible now?
Yes, sir, your voice is audible.
Okay, now I'll share the screen.
Yeah.
Okay. Please keep your mic on, okay?
Yeah, yes, sir.
I hope my screen is also visible now.
Yes, sir. Now it is visible.
Yes, sir.
Just a minute, just a minute. Okay. Just a quick confirmation. The slide is visible and I'm audible well.
Yes, sir. Yes, sir.
Yes,
Okay, cool, cool. Okay, thank you very much for inviting me for this particular STTP, and thank you for the kind introduction. So without wasting much time, I'll start my presentation, which covers the topic on application of image analysis in civil engineering. So now if I ask you like what exactly we use this image analysis for? So we have seen during COVID time, the Russians have made a very good use of, image analysis by capturing those who are moving on the roads. They capture the photos, and based on the features of the photos, they identify who is the person who is violating the rules. Similarly, we have also seen that, nowadays, if we, violate the traffic rules, directly we get the challan at our house also. This is also they make a use of image analysis. Then in engineering applications, if I talk about, initially started with fluid mechanics. There we wanted to understand what is the nature of the flow, whether it is a laminar flow, turbulent flow, moreover the characteristics of flow and how that particular turbulence is occurring, eddies currents forming, in all those things it was used. Later on, it was applied to field of geotechnical engineering as well as structural engineering. Nowadays, it is also applied in the field execution of the work also. Now, this is we are very much aware about the stress strain curve of a mild steel. We have seen that particular stress strain curve, something like this. It is in the linear elastic zone, then it's enter into the plastic zone, the lower end pole, upper end pole, and then it enters into that particular the failure zone. So when it forms over here and it goes down, this is what point we call it as a failure point, and that is the ultimate stress. However, these stress strain curves are not the true stress strain curves, because what happens whenever we do this particular stress strain analysis, we consider the diameter as constant, and based on the elongation, we consider the change in diameter. But actually, we are not measuring the stresses at this particular necking formation, because of which what happens, our curve actually after reaching to ultimate stress, it goes down and enter into failure region. But in reality, it is not like that, because whatever the load is there, it is divided very small area. So actually where exactly the failures are occurring, where the stress strain curves actually goes up. So always stress strain curves goes upward direction. Okay. But most of our theory and our civil engineering is designed on based on this particular area. That's why we are not concerned about this. But nowadays we are talking also about the performance based design, where we exactly want to know how exactly our steel is going to fail. In such cases, we may also have to understand what is the true nature of stress strain curve. So that is possible using image analysis. If we start capturing the photographs and if we see how the diameters are changing, and if we exactly evaluate the load versus area at this particular location, will be able to even see the stress variation within that particular mild steel bar. Now, if I talk like what are basically images, we have used the old time when I was a kid in school. I used to use a phone which is having VGA camera. So we used to get photos something like this. And nowadays, the technology has become so we hold such a powerful camera with our, in our mobile phones. So we get this type of photographs. Now, what exactly is there? If you zoom in the images, they're basically all squares. They are all square, and every square is associated with one particular color. Altogether, if we see it from far, we'll be able to visualize that first image. Now, if I arrange one particular IGS logo according to their size, different pixel size. Higher the pixel size, more will be the clarity. Lower the pixel size, the clarity will be less and we need to represent it as small also. Now let me take this particular image and zoom it to this particular level. You can see when the image is zoomed, the pixels are breaking. It is basically nothing but what a matrix of all these particular numbers. Now what happens when we do this image analysis? We do not want a matrix of color in the in the 3D matrix. So what we do, we convert it into black and white color. We convert that image into black and white. Moment we convert into black and white, your 3x3 matrix, which consists of red, blue, and green color, it's converted into black and white color. Now it is in black and white color, the number associated with black and the number associated with white, it ranges between 0 to 255. Now, suppose if I have a image which is completely black color and there is one white dot. So basically, if I convert into all those of this into grids, and I can represent as what a matrix. If I represent as a matrix, the number over here will represent as almost 250 or 255 as a white dot, and all those numbers, if it is a pure black, perfectly black, it will represent as 0, 0, 0. Now, if I change the position of this particular white color in that particular image, the position of the number in the matrix also will change. See, the position of the number is also changing in the matrix. So can we convert this particular change in position of this number in the matrix as a position vector of the matrix? Yes, we can do that. And if I convert it into position vector, and if I assign a scale to this, can we convert that position vector into a displacement vector? Yes, it is possible. That is nothing but your image analysis, with the help of which we are able to evaluate certain outcome. Now, this is a typical flowchart of any image processing, especially if I talk in context of experimental work. We need an experimental setup. We need to represent our experimental work into 2D representation, to visualize the failure plane or any such thing. Then we need to have one particular track in which we are going to do the experiment, which is going to have a viewing window through which we are able to see the things. Then there is a requisite of any DIC, that there is a need of camera, LED light panels, computer acquisition system. Then we need to optimize the outcome of DIC by using some sort of seeding method. We need to have a precision and accuracy associated with the output. And then we need to capture the photo at every frequent interval of time. And there will be first image and last image captured at a certain frequency. Then all those photographs which are captured, we superimpose all the photographs and we convert every set of images into position vector, and we superimpose all the position vectors to get the output. And when we do this image processing, there is a region of interest over which we analyze. We need to discretize into small patch. We need to do certain pre-processing, post-processing, and the results can be obtained to see as a visualization or also to see as a measurement if you are going to scale it. So every aspect I'm going to discuss very much in detail over here. So let us discuss about the experimental setup. If suppose you are interested in geotechnical engineering to determine the load displacement plot, this is the plan which represents a tank which is filled with sand and over which I'm going to do certain penetration test of a ring footing. Okay, but if I want to visualize the failure plane, then I need to represent the half cut of this particular ring footing, and there will be one glass over here. And there will be position of camera, LED light panels, controlled completely by a computer, through the help of which I can visualize when this particular thing is penetrating into the sand. I'll be able to visualize from this side the failure planes. Okay, so these are all the half cut model of all the geostructures. Okay, and these are all the full model of the geostructures. Now, if I talk about the seeding is what? If any image analysis I'm going to do, what I'm going to see through that particular viewing window. If that particular grains, if I talk about geotechnical engineering, the sand grains which are there, or I can say any of the soil which is there, that natural texture associated with that particular soil is more than enough to carry out the image analysis. But what if the sand is completely white in color? What if the sand is completely black in color, like Ennore sand, the Indian standard sand, which is of more in the of white in color. If it is more white in color, the number associated with that will be more in the range of 250. Okay, so if the numbers are fluctuating between 250 and 250, we will not be able to discretize them. So we do is what we impart an artificial texture to it. Well, how do we do that? We do it by seeding. So we take that particular sand, which is original sand. We take some soil out of that and we color it. After coloring it, after it is dried, we take the original sand and this dyed sand. This color sand is now called as dye sand. We mix it into proportion and we create a matrix, something like this. And if we do the image analysis on this matrix, we are going to get a very nice output. And many times what happens, if we suppose you are going to do this image analysis over any materials like steel. So if you see steel, it is of one particular dark gray color side it will be there. If I keep on capturing the photo, what are the deformations which are going to occur? The number associated with that will be around in the near to 0. Let's say it is in the range of 10 to 15. If the numbers are fluctuating in that, we'll not be able to convert into displacement vector. So we also impart a particular texture to it. So we spray it. We spray it on that. If suppose we want to do some test on geotextile, again, some black color paint is required, or either we can take a pen and we start doing a marking on that particular geotextile. That is also possible. Otherwise, if it is a concrete cube, there also we can create some particular texture, not a rough surface, but over a visualized structure in such a way that the numbers are fluctuating at that particular point. And if any changes are happening, we'll be able to identify that those changes. Now, this is that particular reason. If suppose if I have a sand, which is Indian standard sand, okay, it is completely off-white in color. That the sand what you are using it for concrete testing, cement testing, that white color sand. So that particular sand, if I capture a photo, it will look something like this. Okay, so now if I convert into completely a black color sand, if I capture a photo, it will look something like this. And in between, if I keep on mixing these two things, natural sand and then this particular black sand, and if I keep on adding black sand in increasing proportion, if I capture the photo, it will look something like this. So this is what is called a seeding ratio 0, means there is no sand in that dye sand. Seeding ratio equal to 1 means what? 100% sand is black color sand. Now, when we capture any photos and we convert into black and white and we see the histogram of that, then if suppose it is completely white, that your particular histogram will be skewed to the right. Okay, if this first image, if I determine histogram, it will be skewed to the right. And this last image, which is completely black in color, if I determine histogram, it will be skewed to the left side. Now, if suppose if I make a matrix of this and even evaluate this particular histogram, it will be more on the normalized side. So if I determine the standard deviation, it will be less. Here also it will be less, but somewhere over here, which is having a wide range of color, the standard deviation of the pixel value will be very high. So that means indication of an optimized seeding is what the standard deviation, it should be highest. So if I suppose there is no seeding ratio, the standard deviation was something like this. And if I keep on increasing by 10%, 20%, 30%, 40, 50, 60, and 100%, the standard deviation kept on increasing. After that, if it is more dominated by black side, again, it will start reducing. So if I do my image analysis at this optimized value, I'm going to get the most precise and accurate result associated with that. So now let us talk about the type of camera. So we have two types of generally camera. The sensor which are used in the camera are CCD, that is global shutter arrangement, and CMOS camera, which generally all the DSLRs has. They are all roller shutting arrangement. What does this CCD camera does is they capture the photographs like this from whole to center. Whereas if I talk about CMOS camera, they capture photographs something like this from top to bottom. Now, if suppose we are doing some analysis which is not that sensitive to time, okay, in that case, we can go ahead with CMOS camera. But if suppose it is very sensitive to time, then we can go for CCD camera. For an example, if suppose by the time I'm lifting this tank from top to bottom, like, from top, I'm taking it down. By the time the photographs are captured from top, and when it is capturing from bottom, something changes and the top will not be able to capture. For an example, if suppose you are capturing a photographs of a moving fan, okay, and if we capture it, then it will look like the fan is moving, but in reality it is not moving. When we capture the photo at one frame, it should be appearing as a still, but it is representing it is a moving. That is because of that particular camera at what particular rate they are capturing the photographs. So we have very high speed cameras also that can be used if your output is sensitive to time. Now we have also this type of cameras in which they are called as mirrorless camera. It is just nothing but the reflectivity of the light. We make a use of reflection in our conventional cameras. In this case, directly whatever the light source we are getting, we're directly taking, taking information of that and we are using that. So the sensor is not changing in either of the camera. Only the thing is the way we are capturing the light, and because of which we can optimize the size of the camera. Now, to see whether the output of image analysis is accurate or not. So what type of test we carried out? We carry out rigid displacement test. What is this rigid displacement test? Let us have a tank which is filled with particular sand and it is lifted by 10 mm. Okay, the tank is lifted up by 10 mm and there is also a dial gauge which is capped over here. So if suppose the dial gauge is reporting a displacement of 10 mm and if I perform the image analysis, what displacement the image analysis is giving? If we compare all those at every frequent interval of displacement 1 mm, 2 mm, 10 mm, 12 mm, we can actually develop this type of chart. Means what? A vertical displacement which was obtained from dial gauge, that is an actual displacement, and vertical displacement which was obtained from image analysis. And these are the numbers which I got it over here, which with this I came to know the error associated with that is hardly 1.5%. Means what? From 1:1 positive 1.5%, negative 1.5%. Means overall error band is 3%. So prediction interval is 97%. For an example, when I perform the rigid displacement test and then at a vertical displacement of 6 mm, it showed the image analysis showed a vertical displacement of 6.05 mm like that. Now, this is the history of image analysis in geotechnical engineering. Initially, in 1920, that time, they were using X-ray method. What they were doing, they were taking metal particles, they were putting into sand, and then they were kept on taking the X-rays at frequent interval of time, which is very harmful and very complicated also. And when the penetration is happening, how the particles are moving, we get different X-rays, we superimpose on them, and if we roll, we'll be able to see the vectorial displacement of that particular metal particle, which was not possible in case of centrifuge as well as harmful procedure also. So thereby in future, what people started doing is they started using a viewing window, a transparent window through which they were keeping cameras and they were making a grid of lines into that particular sand and they were taking photographs and they were superimposed photographs to see, roughly identify the failure plane, but they were not able to make any measurements in that. In this particular century or initially start of 2000, the researchers started working on this. Can we evaluate the change of position vector from that? Can we evaluate the displacement vector? And can we make use of that to get the failure patterns and the measurements also? That is how that image analysis started making a wide use in geotechnical engineering. So basically, if I talk about use of image analysis in experimental geotechniques, we are only having two purposes, either for visualization or measurement. Visualization means what? I want to visualize, okay, how the entire thing is going to move, what will be the failure zone? If the soil particles are going to move, are they going to move outward or they are going to move outward and going to roll inside? All those mechanisms we want to see. That is what is called as visualization. Measurement means what? You are not only interested to see how the failure planes are moving, but also you want to quantify the dimensions of the failure planes also. That, okay, at this particular displacement, this was the size of the failure plane. This was the magnitude of the displacement. Like all those measurements, if you want to do, then that is what is called as measurements. Now, this is the literature associated with the application of image analysis, especially in geotechnical engineering. According in Terzaghi, for the shallow foundation, researchers have studied what is the effect of soft boundary, how the street footings are going to settle. If the foundation settle, especially rectangle foundation pushed into sand, what will be the flow mechanism? So this is one of the example of the soft boundary condition. What is the meaning of soft boundary condition? We know Terzaghi theory that it says that the particular size of the failure plane should be minimum 3B on the left side, minimum 3B on the right side. Overall, we consider as 5B, but generally it is around 3B. So if my boundaries are constrained less than 3B, how the failure mechanism is going to completely change, that was studied by image analysis. You can see nice is the failure plane which is obtained over here. And because of that particular constraint boundary, how this particular failure planes are changing, that is what is studied here. Then researchers, what they have done, they wanted to study the macro and micro analysis. What is the macro and micro analysis? If I want to capture the whole information together, so my one camera will be there, only it will capture the entire thing together like this as a whole path over here. And they will analyze the entire domain. Someone's mic is on. Hello.
Yes, sir. Muted. Kept it on mute.
Okay, am I audible now?
Yes.
Okay, now there is something which is called as microanalysis. What is microanalysis? If I want to capture this entire information and if I'm very much interested in very small region what is happening, at that time I can also assign one more camera to it and only I'll capture those informations which is over here. So there is something called as macro analysis and there is which is something called as micro analysis. See, these are the results corresponding to macro analysis. These are the minor information which is captured through micro analysis. So in future, if somebody wants to address this, sand migrations, the sand flow particles, the failure planes, how that particular rolling mechanism is happening, the sliding mechanism, all those things in which we can, use multiple cameras also. Now, related to large deformation problems, researchers have also addressed large deformation problems using image analysis, where the uplift mechanism of buried pipelines, deformation of open cation, arching in trapdoor, related to circular open cation. If you are going to provide a tensile testing to geosynthetics, how they deform laterally in that particular direction, non-uniform, the deformation patterns in the geotextile, soil grid interactions, measurement of strains in geogrid, all those things was possible using image analysis. Initially, when we were testing this particular geosynthetic, what we were doing, when we plot this load versus deformation, or I can say the displacement, the displacement was actually of this particular that particular clamps over here, how this particular clamps are moving with reference to that. So we were not considering the deformation, the non-uniform deformation associated into the geosynthetics. So using image analysis, we are also able to capture the non-uniform deformation in the geosynthetic, and where more the strains are dominated, where the strains are least dominated, that zone also can be quantified. However, the research what was done, we need to identify the region of interest. When we identify the region of interest, whatever things are happening in the region of interest only can be captured. But when we do this wide tensile testing, definitely many things will go out of region interest and we'll be compromising on certain output. So we have done some studies in which we were capturing the entire information along with the clamps also, and we were clearly able to identify the entire failure pattern which is happening in the geosynthetic, and we were able to identify that particular displacement variations in the geosynthetic. Then in offshore also, researchers have made a wide use of image analysis, especially to see if the sputkins are penetrating into the clay, how that particular rolling mechanism is happening, whether the clay will go on the sputkins and it will also provide a resistance when they are lifted upward. Researchers have also studied the layered soil. When the layered soils are there, how exactly that particular the failure patterns are going to change. Then based on different geometry of the sputkin, how the failure mechanism is going to change. Like you can see, identify the shear strain variations in that particular sputkin penetration, especially when the sputkins are of different geometries. Then in the interbedded layers, in which there is a sand interbedded between the two clay layers, how that particular failure mechanism is going to change, that was also quantified by researchers. This is very interesting in study in which many times in offshore conditions we identify that there is a sand over clay. And then because of which we want to identify what is the capacity of that particular sputkin. But when we penetrate this particular sputkin, it goes through sand and it puncture into the clay. So there will be one soil plug which is going to form. So overall capacity will not only depend based on the geometry of the sputkin, but also based on the soil plug which is going to form. The researchers have identified the formation of soil plug, and now we can identify what will be the capacity of sputkin based on this particular plug size formation. Yes, through image analysis, this is also possible. Then there have been studies related to tunneling in which they have used this image analysis. We can see as we have seen most of the studies, what they consider is what in tunneling, they either consider a plane strain problem. So it's a 2D representation and they identify the failure plot. But reality, they are always 3D. and the non-linearity associated with the soil heterogeneity, the spatial variations, the failure mechanism is going to be completely different than what we estimated. So researchers have identified the failure zone associated with the 3D excavations of tunneling, in which they have installed multiple cameras to identify how that particular 3D failure plane is going to form. Then other geotechnical problem like the tensile capacity of clay, the dynamic analysis, the surface of the soil and any structure, how they are going to interact, that was also identified. For an example, if I want to see what is the tensile capacity and how the cracks are going to form in that particular soil if it is subjected to tensile loading. So this study was performed in which the crack formation was also quantified using image processing. There are some tests in which the uplift mechanism of anchors was studied based on different types of sand, whether it is a fine sand or coarse sand, whether it is a loose sand or dense sand. We can see if it is a loose sand, the failure mechanism is quite shallow. It is confined well within the soil, not shallow, but confined well within the soil. But if it is dense sand, it is having a global failure mechanism. Then can we do the particle size? We can exactly identify what will the mechanism will be there between the friction between the particles, whether it will be rolling mechanism, interlocking mechanism, semi-interlocking mechanism, sliding mechanism, rolling mechanism. So based on the shape of that particular particles, we can identify that also. If we know that if it is completely spherical, very circle, then we can identify that it will have no interlocking and it will have rolling mechanism. But if it is having this flaky size, then also it will have no interlocking, but it will have sliding mechanism. But something like this, it will have highest interlocking, and the behavior will be somewhat in between sliding and rolling. So all those things also can be quantified based on this particular particle shape. So researchers have converted, they have taken the photographs of the particles, they convert into binary image, that is black and white image, and they have put all that particular circles, which maximum circles can fit, and the perimeter of all the circle will tell what is the aspect ratio of that particular particle, with the help of which people have identified the failure mechanism. Based on certain observations in the field, for example, the soil structure interaction in Chichi earthquake in 1999, there was one particular well foundation and there was a fault structure interaction. Fault structure means what is it? Can we design any structures on the fault? It is actually stupidity to even think of it. We always avoid, but there are certain structures which are called lifeline structure, which has to pass through fault also. In such cases, we have to also study that we also have to see for an option that can we design any structure which is exactly on the fault. So there is one particular this particular structure which is standing on well foundation. So this is transmission line tower supported on well foundation, and because of that particular massive rigidity of the well foundation, the entire fault line was deviated at that particular zone. So based on this observation, researchers started investigating that what if we change the position of that particular well foundation at different location, and when we create an artificial fracture in that particular soil, which is simulating the fault structure interaction. And this particular study was quantified using image processing. We can see the grids of lines which are made, and we can clearly identify the failure zone. Then studies were based also on the uplift capacity of buried pipeline. If you are going to pull out the buried pipeline in soil, and what type of failure mechanism is going to occur, if it is a dense sand, if it is coarse, if it is dense and fine, loose and coarse, loose and fine, and we can identify how that particular failure mechanism is going to change. The researchers have also studied what is the interaction between the structure and the soil, especially taking inspiration from the snake skin. So if we have a teeth of that particular skin, which is on the direction of the failure plane and which is opposite to the direction of the failure plane, how that particular interaction is going to occur, that was captured through image analysis also. Then there are studies on when the well foundation, when the open cations are sinking in the sand, how exactly the failure planes are going to change, and can we quantify the size of the failure plane also? The researchers have studied that part also. Then in trapdoor mechanism, if we have seen Terzaghi has evaluated the mechanism of arching using trapdoor test at that time. But now with the help of image analysis, we are also able to identify the mechanism at which the failure is progressing, the failure is initiating, and what is the size of the failure plane. That was also studied using image processing. We have performed this particular, the failure of a finite slope also, in which this particular failure mechanism was also captured using image analysis, and we were able to clearly identify the zone of failure size of that particular slope. Now, if I talk about the future scope, it has a very good future scope. Like, can we do the seepage problem, and where can we quantify the seepage analysis also? Then dynamic problems associated with geotechnical engineering, then uplift of an anchor, the soil structure interaction like pipe soil interaction, deep foundation, successive land. If one landslide is already occurred, what is the effect on that particular in future on successive landslide? The failures, the finite slope failure, infinite slope failure, all those can be quantified. Now let me come to the point where we are going to talk about the use of image analysis in civil engineering. That is with respect to the field of fluid mechanics, where the studies have been used for occurrence of turbulence, the formation of eddies current, the measurement of velocity of flow. So in measurement on velocity of flow, when I say velocity, it is with respect to time. So I'll be interested to know how the particles are moving relative to each other at a frequent interval of time, with the help of which I can be able to evaluate the velocity at which the particles are moving, overall the flow which is happening. So what I will need in that flow, I will also need some seeding particles. The seeding particles are such a way it is placed in the water, and the water is moved, and we are keep on capturing the photographs at certain interval of time, and through help of which we'll be able to evaluate the velocity at which the flow is occurring, whether it's a laminar flow, turbulent flow, or transition flow. Then researchers are also used for, in wind tunnels, if we place some smoke and how that particular smoke is moving and what type of currents it is, forming, that are also captured using image analysis. Then local displacements in fluid continuum, all those part has been possible. In transportation engineering, it is taken to another heights, where we are also able to do the classification of the types of vehicles, whether we know that passenger car units, we need that particular number associated with the different vehicles. Okay, but there is a limitation on this. They say that, okay, it is sometimes not possible to convert everything into one particular unit and design, because sometimes if the number of the heavy vehicles or light vehicles are dominated, that particular PCU number or PUC number will not be able to reflect the actual the study of the traffic flow patterns. So there the thing has become very easy now. Just install a camera, and based on the size of movement, we'll be able to classify the size of that particular vehicles also. We can also identify the vehicle type. We can also conduct traffic flow study, accidental study, traffic volume study, traffic survey, measurement of deflection of the railways also. So I'll be discussing about this part also. Then in case of solid mechanics, we are very much concerned about the failure mechanism which is happening in solid materials. So local strain material, crack propagation, failure mechanism, deflection, all those things is possible. In geotechnical engineering, already I have discussed very much in detail about all the aspect. And in rock mechanics also, it is moreover related to solid mechanics, where if I do a Brazilian test, I want to capture how the cracks are forming, the tensile strength test, crack formations, crushing, all those aspects are possible using rock mechanics also. So these are some of the literature on use of image analysis in fluid mechanics, especially moreover the flow was quantified. Then these are something related to transportation, where the traffic flow study was carried out. This is related to rock mechanics, in which the localized characteristics of rock, soft rock, then investigation of crack formation during tensile testing and Brazilian testing was quantified. Then in structural engineering also, these are the different applications, especially in the concretes, 1-point bending test, 2-point bending test. We want to identify how the zones, what are the strain concentrations which are forming, that also can be quantified. We have performed this particular test on steel failure mechanism. If I take this particular steel plate and if I perform the failure of a steel plate, can we identify the failure mechanism? So using image analysis, we were exactly able to identify the crack formations also. Then in concrete tubes also can see when we are doing the concrete crushing test, cube testing, we were able to capture the formation of the cracks in the cubes also. So I'll be discussing all those things in very much details also in the form of research topics. Now, this is one interesting study in which, especially when somebody is going to work on the rail, the rail embankment interaction studies. So in that case, there are sleepers, there are rails, there are ballast, sub ballast, and I want to identify when the vehicles are moving with certain speed, at what rate they are giving that particular impact loading, and how these particular rails are responding to that. And I'll be able to exactly carry out at what particular distance I should apply the load. So there are certain prerequisite which has to be quantified. So when the train was moving, okay, so there was a camera which was installed here and it was capturing the grid mark on the rails over here. And when the rail is moved, because of the movement of rail, the vibrations will come over here. It will create a vibration on the entire cameras also. And there will be some noise in that particular output. So these are something noise which are, if I filter out that particular noise, I'll be able to identify at what particular magnitude, at what particular frequency we are able to, how that particular rail is going to create a load. Magnitude is associated with the locations, not with the magnitude of the loading. Then these are some of the tests on concrete beams where I want to see the propagation of failure in that particular concrete beam if it is subjected to 1-point loading. So you can see how the cracks are propagating and they were all nicely captured using image analysis. Then there were studies in which they have tested the metal plate and they have placed some strain gauges as well as a camera and that particular displacement what we are getting from that particular machines also. All those was captured and they were compared here. We can see the load versus the principal strain obtained using camera and the foil gauges and how nicely we are able to capture all those informations. We have done this type of studies in which can we just capture a photograph of any structure and we superimpose all the photographs to get a 3D structure, a 3D structure, which can be later on used for dynamic analysis. So we have done for this particular heritage site and we address one particular simple geometry and one very complicated geometry also. And we were able to get a very nice results. And then later on, the same thing can be also analyzed using dynamic analysis. And one can also investigate what are the critical locations over which there is an intervention required for that particular heritage site. So we have done this particular time history analysis and we were able to determine the different response of that particular structure, heritage structure. Now we have reached a certain maturity of understanding this image analysis. Now we have applied this image analysis to certain problems. So I'll be talking about total 6 research topic. The very first research topic is on open caching that I had done during my PhD time at IIT Madras, where I wanted to understand the interaction which is happening between the cutting edge of the open caching and the soil, especially for the large diameter caching. What do we do when if it is a large diameter caching, the entire caching is supposed to sink very uniformly into the soil. So what do? We do follow this particular excavation strategy. We remove the soil from this in the plan, then from the opposite side, from this side, then this side, then from 5th, 6th, 7th, and 8th. This will allow the failure which is happening at interaction between the cutting edge and the soil uniformly, because of which the entire caching will sink uniformly. But there are no guidelines available on how much deeper I should excavate, how much lateral I should excavate. So all those studies also we have carried out and we have made a use of image analysis to quantify those deformations. So in that case, we have done this particular 1G experimental setup in which we were using Indian standard sand, that is NO sand, which is not having that much, the color associated or a matrix associated with that number. So we did the seeding. So we made a matrix of soil, which is natural NO sand and a black color sand. We mixed it to a ratio. We kept on, increase the seeding ratio, and nearly around 65% of seeding ratio, we were getting the maximum precision. So all the experiments were performed at a seeding ratio of 65%. You can see over here, if it is completely black color sand, the dye sand, the histogram will be skewed to the left. If it is completely NO sand, which is more on the white color side, the histogram will be skewed on this side. And if it is a matrix of both the numbers together, we are getting a normal distribution and we get the maximum standard deviation. That is what is reported over here. So all the experiments were performed at a standard deviation of, at a seeding ratio of 65%. That means 65% is dye sand and remaining percentage of sand, that is nearly 35%, is your anode sand. You can see the matrix of soil in which this particular cation is pushed into the soil, and the series of photographs were captured using camera, and there is a light which is placed over here to make sure that any other reflections, any other the other source of light is not captured, because other source of light, if they're flickering also, all those things will be captured in image analysis and your results will be compromised. So this is the configuration of the camera which we were using. We were using 16-watt LED light panels, and we did this particular test. We pushed this cation into this, and we were seeing how the failure mechanism was happening. You can see there is a bulge in that particular sand which is forming over here. This was all captured using image analysis. We performed rigid displacement test, and the error associated with all the measurement was hardly 3%. That is 1.5% positive, 1.5% negative side. And this is the very first test in which the cutting edge of very sharp cutting edge of 30 degree is pushed into the soil by 25% width of the cutting edge, 50% width of the cutting edge, 100% width of the cutting edge, 150% width of the cutting edge. If the width of the cutting edge is, let's say 20 mm, it is pushed inside by 20 mm, that is 1 time. It is pushed by 30 mm, that is 1.5 times, be like that. And what is the failure mechanism which is happening? So if we use a steeper cutting edge, all the flow mechanism which is happening well within the cation only. That was the first observation. The second observation with respect to different cutting angles, it was 30 degree, 45 degree, 60 degree, 75 degree, and 90 degree. We can see the failure mechanism happening within only. Here also for 45 also it is within, but 60 onward it is somewhat within and outward also, and it is less with the within also and outward also, and if it is flatter one, it is less within, more outward. That is the reason why the Indian standards and most of the guidelines, they recommend the cutting angle should be less than, the maximum angle should be around 45, should not go more than 45 degree with respect to vertical. So that is the reason we should use steeper cutting edges like 30 to 45 degree for getting the soil flow mechanism well within the cation only. So there is no ground disturbance which is observed. So here all together are shown for the magnitude of penetration and the different cutting angles. And also, what if the cation is penetrated into the soil? What will the flow mechanism? Because of the presence of overburden, the soil flow is restricted more on the within the cation than the outward of the cation. And we were able to see when the magnitude of penetration is increasing, the disturbance which is causing outside is least, even though the penetration is up to 150 times if the steeper cutting angle is used, and the degree of disturbance is keep on increasing if you are using a flatter cutting edges. That's why the IS code as well as all the design guidelines, they recommend not more than 45 degree of cutting angles. Then can we make a use of this to evaluate the failure planes? So if I have a vectorial displacement plot, can I convert into contours? See, it is a vectorial displacement plot. Now it is converted into horizontal displacement contour. Means what? Some vectors are going on the right side, some vectors are going on the left side. Left side vectors are represented as a negative window. Right side vectors are represented as positive window. Now, if I convert everything into negative window, means only those displacement which are happening on the left side, I'll be able to clearly identify that particular line which separates the zone where the disturbance is happening, the zone where there's no disturbance is happening. And if I make this particular line, that is nothing but your failure zone. So we have evaluated this failure planes for ring footing also, something like this, where this type of failure mechanism is happening as a function of different radii ratio and different cutting angles like steeper cutting angle of 30 degree, 45 degree, and we have identified this particular failure zone. Now, related to large diameter question, I told you that in the previous slides that I do not know what should be the depth of excavation and what should be the lateral extent of excavation. For that, I performed this particular finite element analysis, and we did this sensitivity analysis that how each and every parameter is affecting the influence zone, that is lateral extent X and vertical extent Y, that X by B ratio and Y by B ratio for a different radii ratio, cutting angle, surcharge, unit weight, friction angle, cohesion. All together, we superimposed and we propose one equation. So we can use this equation directly on the field and we'll be able to tell what is the lateral action up to which I should remove the soil, what is the deeper action up to which I should remove the soil based on what is the radial ratio used in the field, what is the cutting angle used in the soil, what is the cohesion associated in the soil, friction angle associated in the soil, what is the depth of penetration which is converted to surcharge, and what is the unit weight of the soil, with the help of which I can clearly identify this particular x by b and y by b ratio. As these equations were evaluated using finite element analysis, they were validated by performing experiments using image analysis. So we have varied the different radial ratio, cutting angles, magnitude of penetrations, and we compared the actual x by b ratio and y by b ratio and those which are predicted using this equation, and we compared over here. The maximum error is coming around 20% and almost all the values were lying within the error of 15% error band. What is the meaning of 15%? Means 7.5% here, 7.5% upward direction. That means what? These equations directly can be used on the field, based on the configuration of the question and the properties of the soil which is used and what is the embedment which is used. We can use to identify what will be the size of aleocone. So these are the conclusions which are drawn from that first part research work, that the steeper cutting edges restrict the soil flow within only. The flatter cutting edges will have the flow mechanism within and outward. And we were able to evaluate the failure zones using image analysis, and we have validated our numerical outcome, and we did the assessment using experimental studies also. Now I'll be discussing about the research topic number 2, which describes which tells what are the different parameters which affects the outcome of image analysis. For an example, we must be concerned about that where should we position our camera, where should we position our LED light panel, what should be the size of region of interest, what type of sand I should use in the experiment, what should be the color temperature. Nowadays we get different colors of light also, yellow, white, different magnitude of white, room white, this white, so many things are there. Then seeding ratio, whether it is required or not, what is the different relative density effect, assessment of precision and accuracy. If we have different strain rate in the experiment, can it affect your output of your image analysis? If we use a smartphone camera instead of very expensive cameras or DSLR cameras, can we use our conventional mobile phones which are so powerful nowadays? Then can we also evaluate the large deformation problems in geotech techniques? For that, we did one parametric study and one rigid displacement test. In parametric study, we were capturing the photographs at different position of the camera, different position of LED light panel, different temperature of the LED light panel, and one test we performed the rigid displacement test, in which the tank is lifted up by 200 mm, lifted down, brought down by 200 mm, again lifted up by 200 mm. This was series of tests which was carried out, and we evaluated this particular output. So these were the different types of sand, total 8 type of sand which were there, and Indian standard sand is this one. Now it is dyed as completely black. It looks something like this. In the matrix of 60%, it looks something like this. So the very first aspect, that is position of camera. Generally, if I tell you, if you want to determine what should be the position of camera, then we decide this position of camera based on region of interest what you're targeting. So if suppose this is the tank which I want to capture, so I should position the camera as near as possible that entire tank is visible in entire frame. That is what is called as initial position of the camera. Now, if I suppose once the initial position of the camera is finalized, okay, and if I take the camera little bit near your standard deviation, so the entire region which is there, if I determine the standard deviation of this is going to reduce. So that means what? Initial position should not be. I've actually reduced over here. So it will reduce. And if we take this camera a little bit far away, if we once the initial position is finalized, and if we take the camera a little bit behind, because I want to capture additional information on LVDTs or other data loggers or readings and everything at that particular frame only, then I will take my camera a little bit behind to capture the additional information also. So in this case, what will happen? The standard deviation is shooting up. And after that, if we take it very far, it will all be reduced. That means what? My results will be compromised. So maximum backward, it can be taken nearly 1.25 times, not more than that. The second aspect is what? The position of LED light panels. In this particular case, the position of LED light panel is same as where the camera is placed. In this case, the position of LED light panel is taken near to the tank and away from the tank. And the orientation of that particular LED light is kept as face front, 45-degree incline and 90-degree incline. And all those particular cases, standard deviations was evaluated. It was found that the exactly what is the initial position, wherever the camera is positioned, you should also place the LED light panel in that particular plane only to get the most optimized result, as well as when we keep this particular LED light panels at 45-degree, so whatever the reflection which is going to form, it will directly go over here, and from this face, it will be directly going over here. Nothing will be captured in the camera. So we do not get any such type of glares on that particular output. You can see some of the glares over here. So the orientation of this thing is done in such a way that we don't get any reflection in our results, because what will, even if the tank is moving, the reflection will remain in the position. So because of which all your analysis will show wild vectors, not only wild vectors, it will show some faulty results also. Then what is the color temperature? So we use these three types of light: cool white, warm white, and natural white. It was observed that when we use a warm white, your standard deviations are compromised. So results are somewhat compromised. So if you have option of choosing the light, you should go ahead with natural white and then cool white and then warm white. And we did this for different types of sand also. And for all the cases, we got the same results. Now, what should be the type of sand? Many times what happens, the natural texture which is available in the sand is more than enough to carry out the sand analysis. But only if suppose the sand is completely black color, like Tapi River sand in Gujarat, we get is completely black in color. And Ennore sand from Chennai, what we use in cement testing, they are all white in color. See this one, Ennore sand. So in such cases, your standard deviation is very low. So if I create a matrix of black and this and together, the standard deviation is shooting up so high. Definitely my results are going to be more accurate and precise. Moreover, the natural texture available with other sand like Tapi River sand. Tapi River sand, the texture is so nice that no need to provide any seeding. Directly we can go ahead with particular testing. Only if suppose one color is dominated, then we may have to see whether seeding is required or not. The another aspect is on region of interest. What is the region of interest? That if suppose you have finalized that particular total frame size. Okay, this is the total frame size. Now, if I place my camera, which is a little bit far, and if I target a very small region over here, a very small region, if I do the analysis, your results will be compromised. Why it will be compromised? If you see, there's a maximum size, and if I keep on reducing the size of that particular ROI from top like this, and if I go to this one, you can see I can also see the particle shapes also. But when I see the clear particle shapes over here, when the image analysis is carried out, it will do over a small region. So here at this small region where my cursor is there, all the numbers in the matrix will be of same number. So if they are moving, will not be able to identify at how they are moving. So all your results will be compromised in that case. So maximum reduction in the ROI should not be more than 1/4 to the maximum size. If the maximum size is 100, so divide by 4. That is around 25. The region of small interest, the micro analysis should not be done less than 25 pixel size. If you want to, when targeting at a very small region, it is better to take the camera a little bit, towards the tank side and perform the analysis. Now, what happens many times when we do this particular penetration test, even the tests are performed at one relative density, during the progress of the failure mechanism, the relative density of the sand changes. So we wanted to understand what is the effect of relative density on the output. It was observed there is not much effect of relative density on the output. Whereas in Tapi River sand, what happened in Tapi River sand, the particle size distribution, if you see of Tapi River sand, the finer size, okay, the finer size was dominated, because of which when it is dropped to a certain big height, to maintain a higher relative density, the smaller particles were adhering to the surface of that particular viewing window, because of which we were seeing that, okay, the standard deviation is reducing, but it was all because of the particle size distribution. Otherwise, for all cases, the results were almost same and there was no effect of relative density. These are the tests. These are the results now from a rigid displacement test, where we wanted to study that what is the different grading of sand is going to create an effect. For example, if I take a sand which is not seeded, which is 100% seeded, and which is seeded at 60% matrix, where the results are compromised. So here the displacement what we obtain from image analysis and the displacement what we obtain from LVDTs are compared, and it was found that in case of 60% related matrix, the analysis did not had any compromise in the results, and directly at one run only the entire analysis was completed. Whereas if I talk about the seeding ratio equal to 0, some analysis were compromised. So definitely higher standard deviation should be used to get the more precise result. Second thing which we addressed was strain rate. Was strain rate of 1.2 mm per minute to 6 mm per minute. There also we observed there was no effect of any strain rate. Then we made a use of smartphone camera and DSLR camera, and we obtained that the results obtained from smartphone camera and DSLR cameras are almost same, only a little bit compromised with smartphone camera. And the smartphone camera which were used over here was the Samsung with some 50 megapixel camera. So in low budget experiment, definitely one can go ahead with the smartphone camera. Otherwise, one should definitely use camera because we are able to control the ISO and the frame rate and the way it captures the photographs. All those things can be controlled, and without touching to a computer, we'll be able to control the camera. That is possible using DSLR camera. So if you have budget, definitely go ahead with camera, DSLR camera. Otherwise, even with smartphone cameras also, we were able to see the results are almost same. Then can we capture a very large deformation up to 130 mm deformation? The tank is lifted by completely 130 mm. So we were able to get a very nice results comparison, with respect to LVDT and as well as from image analysis. So these are the summary and conclusion that the position of the camera with initial distance should be maximum taken is 1.2225 times than the initial distance to have a more optimized values, and position of LED light panel should be the same as where the cameras are positioned, and the orientation should be from 0 to 45. Make sure there is no glare, and natural white or cool white should be used. Warm white should be avoided. Size of area should not be reduced more than 1/4 size of the sand, which is having adequate texture can be used, and there is no effect of relative density. And DSLR should be used to obtain more reliable and precise result. But in budget experiment, definitely one can go ahead with smartphone cameras, and there was no effect of strain rate. And yes, if you want to address large deformation problems, especially the salt which is moving relatively very longer displace, from one position to another position, it goes a very large displacement. You can capture also using image analysis. Now, this is the third topic in which I'm going to talk about the geosynthetic testing. So we know the geosynthetic are generally used for suppression, filtration, drainage, protection, reinforcement, and barrier. However, when we use it in the design point of view, we consider the geosynthetic in which the deformations are uniform, but in reality they are never uniform, and there is the strain and deformation, like whatever the displacement concentration will be there at some locations. Now, many times what happens whenever we get in geosynthetic, if there is any hole, if there is any slit, if there is any defect, what will be the effect of those particular defects on the failure pattern or a failure progression on the load carrying capacity of the geosynthetic was captured. So here, this is the test setup in which we have used 3 different types of geosynthetic. Woven one, that is like how our cottons, whatever the clothes which what we are wearing, they are all woven. Okay, we can see all the threads are in one line. Non-woven means what? They are all interlocked among each other, and they are all non-woven. So we have used 2 non-woven of different thickness and 1 woven, and we did this particular test in which this is that intact non-woven geosynthetic. We played a inclined slit, 45-degree inclined slit, horizontal slit, and vertical slit, and we were able to see how that particular failure planes are happening. For this also, as this particular geotextile, which is completely white in color, we need to give a texture. So we were using black spray. So we were putting spray on this, and we were capturing the photograph, and we are increasing the concentration of that particular spray, and we will keep on capturing the photograph. So we can see as we are increasing the spray at this 25th image. After that, the values are going down. So what we did, we kept that particular sample of 25 image, and that was the most optimized seeding that was done on that particular geosynthetic, and that is what we used in our all experiments. So this is that particular geosynthetic, and ROI is masked over an entire region, including the clamp also, so that even if the geosynthetic is displacing out of ROI, whatever this particular results will be there, it won't be compromised. So this is the validation in which we evaluated the displacement from the clamp, but extensometer from the machine readings, and from the image analysis, and we compared our results over here. You can see over the light green color is cross-head displacement from the extensometer. This particular line is the displacement from the machine which is rolling. Based on the rotation, we can convert into displacement. And then from image analysis also, we compared all the results. We can see how nicely that all these values are matching, which says that the output of the image analysis is accurate, almost accurate. Then these are the three different types of geosynthetic which was used. BOO1, this is BOO1, and these are all non-BOO1. So very first test which was done on BOO1 geosynthetic, as they are all fibers, like all nicely placed threads in that particular this particular form. When we capture all the deformation which was happening was like non-uniform, and it totally depends on how we are gripping it. Based on this gripping, we were able to identify the vectorial displacement plot and contours also. The second thing is on BOO1 geosynthetic. We can clearly identify how nicely the necking formations are forming. We can see the necking formations which is forming in this particular geosynthetic. Then this was another geosynthetic, non-BOO1, but thickness was 350 GSM. Here also we were able to identify the entire necking formation and non-uniform displacement of the geosynthetics, non-uniform displacement contours. Now, the magnitude of necking can be evaluated by taking a point at this location, taking a point at this location, that is A point and B point, and how A point is moving and how B point is moving and how B point is moving. You can see B point is not moving laterally at all. That means it is remaining in the position. There are no horizontal vectors, but with respect to A point, there are horizontal vectors, and this one we can identify the magnitude of necking also which is forming. This is the magnitude of necking which is formed in that particular geosynthetic. These are the ultimate loads what we obtain from slitted. Means this is one, it is intact. This one is vertical slit. This one is inclined slit, and this is horizontal slit. Definitely horizontal slit, that is slit parallel to the direction of the loading. In direction of the perpendicular to the direction of the loading. Definitely it will initiate the higher failure mechanism, because of which the load capacity is reduced, and whereas the vertical slit is having less reduction in the load. And these are all the different failure mechanism which is happening for different position of that particular slit. If it is an inclined slit, vertical slit, no slit. So if there is no slit at all, the failure was happening at that particular junction where it was clamped. So this is that particular location, the failure progression with respect to horizontal slit. You can see if there is an horizontal slit, how the vectors are also changing over here. If it is vertical slit, you can see how that particular from here, how the vertical failure slit is having progressive failure mechanism. You can identify this particular vectorial contours also. The another one is inclined slits. You can identify how that inclined slit failure progression is going to occur. So overall, we were able to capture the non-uniform displacements in the geosynthetic, as well as even if the entire ROI is captured over the clamp also, we were able to identify the entire complete failure mechanism into geosynthetic. Nothing was going out of ROI, and we were able to identify that also, that if it is horizontal slit, the results, the capacity is going to be compromised more compared to vertical slit. That is totally depends on the direction of the loading. Now the fourth topic which I'm going to discuss about, it is efficacy of image processing experimental research, especially related to concrete testing, steel testing, wooden structure testing, geosynthetic testing, as well as soil structure comparison. So here the very first was on concrete cube. We sprayed that particular surface of the concrete using a spray, and we were able to identify the optimized texture. And then we did this particular test in which the spalling of concrete was captured over here. You can see all the failure which is happening over here, which was captured. The another one is the steel testing. If we do this particular steel testing, we kept all the different position, and we identify the failure of that particular point. So here we kept this particular reference plate over here, which is having a rigid displacement. So directly the displacement what we got from LVDT, dial gauges and PIV, they are exactly matching. And if I determine the PIV displacement at different location in the specimen, they are all coming as different locations, we can clearly say is that the deformations which is happening in the plate is non-uniformly distributed in that particular specimen. So these are the results where we were able to capture even the crack formations also into that particular image analysis. This is with respect to wooden block. Wooden block, if it is tested, we were able to capture this particular deformation. But moreover, the slippage in wooden was observed. Then we had this particular geomembrane. Geomembrane is one of the geosynthetics in which they are used as a suppression material. So they elongate a lot when we do some testing. So what are the deformations which is happening, that also was captured in that particular geomembrane. So this is a UTM testing of geomembrane, where nicely we were able to capture this particular non-uniform deformation, the necking formation. So these are the efficacy of image analysis from this testing of steel plate. The error was not more than 3.8%. In case of geomembrane also around 3.5%. But in case of wooden block, what happened because of the slippage? The load is with respect to clamp and the PIV is with respect to wooden material. So because of which the results were having more errors. So one understanding we observed over here that there should not be slippage in any of the testing, because when we are going to correlate with respect to load and displacement. So because the LVDTs and everything is placed at the clamps, not on the material. So this is how the results are more compromised when we have the slippage. So overall, if I conclude over here, it is based on that particular material testing. We were able to do the testing on steel plate, concrete, geomembrane, and we were able to identify the failure propagation. Now the fifth part is on failure plane of strip anchors, which I talked earlier in the that last object is on structural interaction. That if I have a strip anchor placed over here and is completely filled with sand, and if I want to see the failure planes, so when this particular entire thing is lifted upward, how the failure plane is going to change with the different position of the anchor plate at 2B at shallow embedment, 4B at its little bit deeper embedment, and the relative density of the soil is changed from 15% to 50%. So these are the results for 15% relative density. And here we have played one reference plate over here where we did this particular image analysis also. So we got the displacement from the experiment and we got the displacement from image analysis at this performance, this location. And they were exactly matching. This is how we can do the validation also. So because here in this case, we are not able to position any LVDT on that particular location, and we were not able to lift the entire tank to see the rigid displacement because the size of the tank was 1 meter and it becomes very complicated to lift the entire tank and perform the rigid displacement test. So we found out another option of putting a reference plate here to do this particular thing. Now, these are the PIV results from that particular test. And we can see how the failure planes are propagating. That also we were able to capture. And the same thing we performed using Optum G2, that is FEL analysis, and we were able to capture that particular deformation. So these are the comparison of Optum G2 results, and these are the results corresponding to image analysis. Then for greater embedment, which is around 4B, we were able to see the comparison also. This fluctuation in the values are associated with reference to what the load which are fluctuating, because everything is correspondence to the load value. Now what happens when we do this particular test, we know the transition of the failure mechanism of the soil enters into peak state to critical state to residual state. This clearly say it's a single line, it is a peak state. Here somewhere it is a critical state which is happening, and these are all the residual state which is happening. So rolling mechanism, it will have failure of that particular particle, which will have a sudden failure mechanism, because of which the load will keep on increasing and will drop down, increasing and drop down, which clearly indicates the entering into the last deformation state. That is a residual state. And these are the results corresponding to image analysis. And these are the comparison of Optum G2 result, that is FELA, and as well as experiments. And then here we compared all the results, and most maximum error was everything was within 3% error band. Then we compared the output as a uplift factor, which is directly correlated with respect to the failure load as well as the geometry and the properties of the soil. The uplift capacity factor NUR was obtained from image analysis and as well as not image analysis, experiment, as well as the FELA, and we were comparing all the results here. Now the last part which I'm going to discuss is about the failure simulation of finite slope. So there are typically finite slope and infinite slope. And if we want to see how that particular slope is going to fail, we need to perform a centrifuge modeling test. Otherwise, we need to impart some sort of extra loading. So to avoid that in 1G experimental setup, we did is what we rigidly connected everything together. Means what the tank, the camera, the LED light panels, every aspects are connected rigidly together in such a way that when the tank is lifted from all directions, all the LED lights, all the camera, everything is having a rigid displacement, the same as what is there of tank. Overall, if we capture the photographs, all this in series, what happens is we see everything is horizontal. And when this failure mechanism is happening, you can see the video, try to see both the things together. Okay, from top and bottom over here, see how the particular failure mechanism is captured, and that thing can be analyzed. See, when this particular failure zone is happening, we took this videos in this because the failure is so sudden. If we keep on capturing the photograph at a certain frequency interval, at some failure point, which we do not know when it is going to fail, will not be able to capture the information. At that time, high-speed cameras, which are having maximum number of frames in per second, can be used. So you need a very good source of light. In all such cases, when the lights are also emitting, they emit at certain frequency. The photographs are captured, they also capture at certain frequency. That should be taken care when we do all those things. Then we perform the image analysis in that particular failure. We can see this particular failure and we were able to identify the size of the failure plane also. So these are the comparison of results from, we did a numerical analysis also. So these are all the results corresponding to the image analysis. Then what we did that we wanted to see, can we get the failure plane and how the failure plane is going to move with respect to time using numerically. So we have used a higher advanced numerical modeling, that is like advanced arbitrary Lagrangian Eulerian approach, through which we were able to capture the deformations which is happening in the finite elements. So when we use a conventional FEM, this is what the mesh discretization is distortion is happening, and we are not able to capture the way the soil is failing. So what we did, we imparted one predefined failure planes and based on experimental work, and we did this particular test. Then we were able to clearly identify using numerically that how can we get this particular failure propagation, and we compared the results with numerical output that at 0 time interval and at different time interval of 0.26 second or 0.26 second, what we got the results from actual experiment, from image analysis, and from the numerical. And these are the comparison of horizontal displacement with respect to time, where without slice, this is what the deformation we got. And here with slice in ALE, we were able to have a nice comparison between image analysis and this particular output from ALE. So here I have discussed my total 3 research topic. We have seen initially the way image analysis actually works. What are the applications, especially in geotechnical engineering, in civil engineering? And then we discussed the applications of that for 6 research topic. Now we are going to discuss something related to if you want to do make a use of image analysis, what exactly you will need. So when you do this particular test, you need to make a dark room, because what happens if there is a light and if we capture the photographs and whatever this light reflections which will be there, which is going to come over the viewing window, which will be captured in your experimental in your camera. And now even if the sand is moving, the reflection will remain in the position, your results all will be not accurate. In that cases, we do not need any external source of light. So we need to make sure that when the experiments are performed, all the windows and everything is closed. They are completely covered with curtains. Even small gap is also completely filled with black paper. You completely make the room as dark light. Place the LED light panels in such a way there is no reflection which is coming in the entire experiments in the camera. The camera should be positioned based on what ROI you are targeting. The experimental setup 2D should be 2D representation. If you're using sand, then seeding can be done. But if you're using a clay, the seeding is not possible in case of clay. So what do we do? After making a clay bed, we remove carefully the viewing window. After removing the viewing window, we take a flock particle. What is this flock particle? Either they are plastic particles or our wood sawdust particle that we sprayed on the surface of the clay. And again, we place back the viewing window. Before placing back the viewing window, we put a transparent jelly. Okay, a petroleum jelly or transparent jelly, such that when the clay particles are going to move, there is no friction between the clay particles and the viewing window. So only a plain strain condition has been obtained. So in case of clay, this is how we do. Then when we do want to analyze only for visualization, directly proceed, nothing is required. But in case if you want to quantify the measurements, you will need a correlation between the actual dimension and pixel dimensions. So you need to have an actual dimension in X direction and the actual dimension in Y direction at different discrete locations. So what do? We keep a reference mark that is called as control points at every grid points. It's a, let's say the entire tank size is of 1 meter by 1 meter. So every 150 mm interval, we put a control points. On this particular control points, we know the actual dimensions. So through which we scale it, the pixel domain as well as this image space domain, we scale it. Now optimum seeding ratio. For that, we make a use of Photoshop to determine the mean standard deviations to. Sorry, Photoshop is used for marking the control point. Optimum seeding ratio, generally we determine the standard deviation of every photograph obtained, and then at different seeding ratio, and wherever we are going to get the maximum, the value of standard deviation, that is nothing but indication of optimum seeding ratio. When we capture the photographs at what interval, so generally it depends on the strain rate at which you are going to capture you're going to perform the test. So there is some prerequisite which is required, you need to do it. And based on that, you decide what interval you should do. Generally, in my experiment, I generally go for a displacement of 2 mm to 5 mm per minute strain rate. And in that case, every 2 to 3 second interval, I capture photographs. In case of video, the frame rate is very important, especially if the flow mechanism you want to capture is very much dependent on time. Then when to use CCD, if it is function of time, you can go ahead with CCD, high speed resolution camera. Otherwise, CMOS sensor is more than sufficient to go ahead. Now to begin with, there are open certain sources which are available. So this GeoPIV RG is completely open source MATLAB based program, which you can download from this particular link. I'll share this PPT to Arbaz sir. He may also share it with the participants, those who want to make a use of this particular image analysis. There are other certain algorithms which are used. This is GeoPIV, the PIV view, VIC, GeoPIV RG. This is what I have used in my particular study. VIC, image J, correlation. So GeoPIV RG works more on the photographs what we capture, and there are many other softwares in which analyze the videos also. So one can go ahead with that also. So this is that GeoPIV RG. When you go to that particular link, this is how it is obtained. You can download the software. There are procedure. There are guided videos available how to begin with, and you can actually do some tutorials in that, and you can begin for your particular experiment also. To begin with image analysis, you can refer all these papers in this particular order. There's a review on digital image correlation and experimental geotechniques published in India Geotechnical Journal. Then recommendation on DIC technique, which is published in Geotechnical Testing Journal. Observation of tensile testing of geosynthetic, published in Geosynthetic International Journal. Then the failure mechanism in circular open cation. And these are two papers on failure mechanism published in International Journal of Physical Modeling in Geotechnique. And there is another paper on evaluation failures on sand beneath ring footing and cutting gauges that is published in Indian Geotechnical Conference. These all papers can be referred to begin with image analysis in your particular experimental setup. So I thank one and all for patiently listening to me and the organizer for giving this opportunity. Here is my contact details. I work in the area of computational geomechanics, especially related to the failures in the geostructures. Then physical modeling and use of PIV, that is what I've discussed today. And one small glimpse I showed related to heritage conservation, in which we work on the geotechnical aspect as well as structural aspect of heritage conservation. Thank you one and all for giving this opportunity, and I'll end my presentation here. And the forum is open for questions. If there are any questions, please feel very free to ask. Otherwise, you may contact me also. Over to the organizers, please.
Thank you, sir. Participants, if you have any doubts, if you have